Good morning, everybody. Can you hear me?
Yes.
Okay, great. Did we see the materials for the lab today on Moodle and the video?
Yep.
Good. Thank you. So today we'll look at the concluding part of our chapter 8. And by Friday, we should be able to move to chapter 9. We just want to be able to cover what we should before the break and then the test. Okay. Okay, so today we want to look at compression and stretching and compression of materials. Okay. And this is just one of the things we'll be looking at today. So we just want to start with stretching and compressing materials. When we looked at a catalog of forces, we described the normal force. We used the analogy of a book resting on a table. And that was the first time we tried to get familiar with the word compression. We described that for force such as the book resting on the table, there's a little compression. And then we also saw the spring force, where it is evident that there's a compression and stretching. And in our very last class, we saw compression when we used it to describe, or we saw stretching and compression when we used it in terms of the spring. We defined the Hooke's law, and then we saw the spring constant. So we want to go further to the stretching and compression of a rigid body or a more stiff system. We defined rigid body before as that body which does not change shape or size when it's in motion. Okay. So discussing compression in terms of rigid body, let's take the analogy of the steel rod in the figure A and B. So model the steel rod, for example, like the particle model of a solid. And you see the hand pulling the steel rod. And whenever there's such contact, there will be compression, but in terms of rigid body, it's not as visible as that of the spring, where you can easily see the size changing. But what actually happens to the particle of the rod when there's a force? There's actually, depending if the force is pushing or pulling, there's actually a kind of compression or enlargement or stretch of the molecules or the particles of that system. As you can see in figure 1, sorry, we see the hand pulling the rod on this side. We want to describe the stretch. We change in L. In our last class, we describe F as K change in X, but we are using change in L in the same length as change in S, okay? So we have the force, we have the change in L, the force. Then we can see also trying to enlarge what happens to the particle of this rod. That is the picture you see here. Okay. So we can see, enlarging that molecule, we can see the stretch, little stretch. It's not noticeable, but it exists on the atom or the particle-like atom, so that it's stretching like spring. Okay. So that when the hand releases it, there will be a restoring force, a compressing process will happen. Okay. Now, because the stiff system has the ability to stretch and compress, we will also say it is elastic. We saw that in our last class where we defined the restoring force as elastic, ability for the object to return to its original length. So we also have such experience with the stiff or rigid body. It has the ability to stretch and to contract. We have other examples like the common one that we used to say, the steel rod on your bridge. As the vehicle passes, it's going to be stretching and contracting, or stretching and compressing. Okay. So like the spring, we'll have that the restoring force is proportional to length. So the restoring force, that is what takes us to the figure B here, where we can experimentally measure that little change in L. I know for stiff body, that is the body that is not easily responding to stretch or compression, or visibly responding to stretch or compression, behaves like a stiff spring. We have the force of about 16,000 Newton, just being able to produce small stretch of about 1 millimeter. Okay, you can see that it is about 0.01 meters using 16,000 Newton force. But in the case of spring, just little force will yield large stress and large compression. So when we experimentally made the plot of the force against the stretch for rigid body, such as steel rod, we saw also a linear relationship, just like we saw in the case of spring. Therefore, the slope can actually give us the K, and you know what our K is, our spring constant. Okay, our K, that is the ability to stretch, but in terms of spring, we just say spring constant. All right. So for this kind of material that don't easily, any material that don't easily or visibly respond to stretch and compression is called rigid. So let's look at further understanding of this. If we call the material that does not easily respond to stress and compression as rigid, materials such as spring, rubber, or elastic material sort of, that is such materials where you apply small force with large deformation or visible stress, we call them planes. So we have in this system of stretch and compression, the class of material called planes and class of material called rigid. This one, large force yields small stretch or small expansion, while this one, small force yields large deformation or large expansion. So we have seen in this case as that of spring where K will have F equal to K change in X. But for this rigid body, we'll have the K to be given as YA over L, where our Y is called the Young's modulus. And what is Young's modulus? It is actually the property of material, such as the rod. So that means the property of that material that makes it easily stretch or compress. So from the rod, The Young modulus does not depend on the shape or size. It actually speaks about that inherent property of that material, ability to stretch and compress. Okay, so if this is our K, and in our last class, we have seen that F, which is proportional to, in this case, we are using L, all right, which is the same thing as changing S. Then we'll have removing the constant of sign of proportionality. So we'll substitute the value for K here. That is how we arrive at this equation. Okay, so we put K into this relationship. We arrived at this. Remember the K, the constant, which is the compression stretch constant, is bringing in the term Young modulus. Okay, so that is a new thing we introduced here. It's not different from the stretch and compression you've seen before, but for rigid body, we have brought in this Young modulus. Now, rearranging this equation, we can see a ratio here and a ratio here, and the Young modulus serving like the K. So we can actually say that the ratio of the of force to cross-sectional area, F over A, which we call stress, is proportional to the ratio of the change in length to the original length, which we call strain. So we'll see on this side the term stress, and we're seeing on this side the term strain. So what is stress? The ratio of force to cross-sectional area, and strain, the ratio of change in length to the original length. And when they are expressed together, we see the formula for the stretch of a rigid body or the compression of a rigid body. So it's either it's stretching or it's compressing. So that is what we explained the Young modulus to be. Now, for the spring constant of rod, that is rigid body, we actually see that it depends on three major things. We can see the force. We are seeing the cross-sectional area that is from this diagram. This is the cross-sectional area. This is the change in length, and this is the force, as we saw in the first diagram where the hand is applying the force on the rod. Okay. And another thing to note here is the longer the rod, the better it is to explain or see the stretch and strain. Okay, because if it's going to take about 16,000 Newton to get a stretch of just 1 point or 0.101 meters, you know what that means. If you're reducing the size, you will have a stretch that is negligible, that you cannot even notice. Okay, so we can see the unit of stress taking the unit of these two, which is Newton per meter squared. And because this length meter over meter will cancel, this makes the ratio here, strain, to be dimensionless, all right? So it has no unit. Therefore, Young modulus takes up the unit of stress. So the Young modulus just takes up the unit of stress, as the change in or the strain is just a fractional representation of the extension of such materials. Okay. So we can see experimentally the Young modulus of the list of rigid materials. We see for casted iron steel, we'll have them like constant. So if you are given a question, most of the times we specify exactly what the value, of the Young modulus would be, or we ask you to find it. Give you every other parameter, we ask you to find that. So if the stretch or compression, if it's due to if the stress, remember what stress is, the ratio of force to A, is due to stretching, we'll have what we call the tensile stress. Yes, I have your hand raised. Amaka, can you come on the mic?
Yes, in the previous slide, it says that force is directly proportional to change in length. But then I don't really understand that if the formula that for force is equals to constant K multiplied by change in X over change in L, isn't force supposed to be inversely proportional to change in L?
Here, what I wrote here, right?
Yes.
Okay. Now, do you remember when we talked about spring constant and we talked about this formula? You remember this formula?
Yeah.
Okay. What change in S mean here is what? The change in the length of the spring, right? If you remember
Yeah.
our last class. So it's, if we replace this with another symbol, say L, where we use X to describe distance, we're using, actually it describes the length. We're also replacing now with L, which is the change in length, original length to the extended length. So if we say the experimentally the K is defined as the Young modulus, product of the Young modulus and area over the original length. When we brought it into this equation, it did not change the change in length. Can you see that?
Yeah.
So this is now your K. So it did not change the definition to inversely proportional to original length. Force is proportional to change in length. This symbol means change, that is a stretch or a compression away from the original length. You get that? Now, the constant K brought in the original length, which gave us this ratio when we rearrange this equation. So the constant K came after the definition. It did not change that definition that the force is proportional to change in length. Do you get, or did I misunderstand your question?
No. I understand now. Thank you.
Okay, it's clearer. All right. Okay. So we'll proceed. We said that when the stress, so stress FA, is due to stretching, we call it what? Tensile stress. Okay. And what we want to emphasize here is that the large value of Y, you know what Y is, the Young modulus, that is that property that describes, that value that describes the property of a material or characterize the material. When it's large, it means that the material is stiff. So for smaller Y, we see that the material is softer. That means it can easily be expanded or compressed. So we see it to validate that here, see the range of value. For iron cannot easily be compressed. Still, look at the value is 20 as compared to wood. Wood that you can subject to certain level of heat or dryness, or even adding water, you see expansion and contraction, easy stretching and compression. For example, if you get your live wood, you cut it, as it gets dry, you see it compressing. There's a way you can process that wood as well. You can also make it enlarge or stretch out. So you see high Y leading to stiffer material. So let's take one example, which is about the only example we'll be taking today. A Foucault pendulum in physics department used to prove that the Earth rotates consists of 120 kilogram steel balls that swing at the end of 0.6 meter long steel cable. The cable has a diameter of 2.5 millimeter. Okay. When the ball was first hung from the cable, now the question is, by how much did the cable stretch? So we'll have our formula before, which is FA Y changing L over L. And we know how this happened. We rearranged it. So if we make changing L the subject of formula here, we'll have this equation, okay? So we just use the same equation of Young modulus, substituting our F, put our K, then changing L, which we rearrange to get this. We made changing L the subject of formula to get this equation. Now, when we looked at the question, we can see that the parameters that were given to us can help us find A. Young modulus of a steel rod is constant, which will be supplied, or if it's not stated here, usually supplied as constant to the constant variables. So we just calculated the cross-sectional area of the cable. It's a steel cable. Cross-sectional area of the cable is the same as cross-sectional area of a cylinder, which is pi radius square. So we converted the 2.5 millimeters to meter diameter divided by 2, which will give us radius. So we use pi multiplied by radius to give us 4.91 times 10 raised to the power minus 6 meters squared. So we have the force, which is given because they gave us the weight. So calculate from the restoring force of the cable, force which is equal to weight, which is equal to mg, mass is given, g is constant, and we'll obtain this force. So now that we have obtained the force, we have obtained A, F, and A. L is constant. Okay. We're looking for the change. We have the original length. So the original length which was given to us in the question is 6 meters. And the question said, by how much did it stretch? So substitute our values directly, and we see that it actually stretched with from 6 point additional 7.2 millimeters when we converted to meters, or converting meters to millimeters. That's what it gave us. 0.00. Always confirm these values, okay? Use your calculator to punch it. Sometimes they vary. So just to be sure you are punching the right way, and you get used to the way your calculator works as well. So we'll see how we have used the Young modulus equation to obtain the stretch for a rigid body. So these questions can actually be varied. We supply a different parameter. We can ask you to find the Y, we can ask you to find L, we can ask you to find the force. Depending on the parameters that are given, you will know the approach to take, okay? All right, so we'll move on to the next thing we'll discuss today, which is beyond the elastic limits. Beyond the elastic limits. Now, we have seen that materials can compress and they can stretch. Now, there's a way you apply force to a stretching material, compressing material. It gets to a point, it becomes permanently deformed. It does not have the ability to return anymore to its original shape. At that point, we bring in what we call the breaking point, that is, that's going to the beyond the elastic limit. So let's take the graph of a rigid body plot here. We'll see the plot of the force proportional to change in length, and the slope will give us the K. So at this defined part, where there's a straight line, this clearly shows this relationship, okay? With K coming in to change this. But look at this region. This is the linear region. Now look at this region where we have the elastic region, where when you stretch, it can actually still, the system is already experiencing a kind of stretch that is tending to go beyond what it can accommodate, but it still can. All right, you notice that the line there is not so linear. So this region is what we call the elastic region. So that beyond this region, that object is going to be permanently deformed. It can no longer go back to its original state. So at this point, where we have the elastic region, the end of that elastic region is what we call the elastic limit. Once it goes beyond the elastic limit, it has entered the breaking point. Okay, so we'll have that every material that can stretch or compress has its elastic region, beyond which it will exceed the elastic limit and then break. That breaking point is a point where it can no longer return to its original form. It is permanently deformed. Okay, so we have at this point what we call the ultimate stretch, where it has taken the ultimate stretch and then it breaks. So we'll bring in what we call the tensile strength. The tensile strength of this material reads from here down, okay? The region from the linear region to the elastic point, beyond which it starts breaking. That is what we call the tensile strength of that material, because it has gone beyond its ultimate stretch. Okay, so such ultimate stress on that material is actually what we call that. So, and that's what we are emphasizing here, that for a rod or a cable, the particular material we use matters, and we can determine an ultimate stress, also known as the tensile strength, that is the largest stress that that material can sustain, beyond which it goes to the breaking point. Okay, so we have seen a tensile strength. We have also seen what we call tensile strength, tensile stretch, stress and tensile strength. So just note the difference between these two words, okay? One is describing a breaking point. One is describing, sorry, I can't find my pencil. All right. Okay. So the formula for tensile strength is actually coming from, if you remember this relationship, this is the relationship for what? Stress, okay? So at the point of ultimate stress, we now have what we call tensile strength. So it becomes the F max here. So tensile strength is actually a description of stress at its ultimate state. So the largest stress that it can sustain is defined by this. We know what our F is and we know what our A is, which is the cross-sectional area of the material. So this is an example of some materials as well with experimental established value for rigid body. Now, we'll see for polymer, for gas, polypropylene, the glass, the casted iron, aluminum, and steel having different value of tensile strength. Now, this information helps us in design, especially technology where we have to make use of electricity and apply heat that can lead to stretch and constraint or compression, and also permanent deformation if care is not taken. Okay, so let's see quickly. How does that play out in biological sciences? I know most of us here we're moving into biological sciences, so this should interest us. Okay, I would have loved to take example here, but you have to look it up as part of what to do. Okay, so let's look at elasticity of biological material. We said that material that has the ability to contract or expand or stretch is elastic, and that is what we call elasticity. We saw that before in our last class. And we have biological materials also exhibiting this kind of processes. Let's take an example for the spider silk and the steel. If you have a steel and a spider stick, and you're meant to apply the same amount of stress or force on them, when you make the plots of the stress to strain, you notice that of the spider stick is more visible, telling you it's actually a plain kind of material, why this is a rigid material, rigid. Okay, so but something happened because we applied the same amount of stress. We see that they both got to the same kind of level of breaking point, but what happened at different strain length, different change in distance. Okay, remember your strain is ratio of change over the original length, but both materials will fail at the same time to show that they have the same stress, the same about the same tensile strength was applied. Now, that is comparing material, biological material and the rigid body. Now let's compare what happens in the biological body, like the human. What happens to the bone? Every time we move about, we subject our bone muscles to a kind of stress and compression. And the structure of the bone has the structure such that the end part is thicker, and in the middle part, inner part, we begin to see some spongy kind of description, while we have the compact bone outside. So experimentally, we use cylindrical shapes to model the shape of bone when studying the stress of a bone. And that is what happened, especially it is prominent in the bone of a bird, like what we have here. The inside is going to respond like the hollow, and the outside responding like the thicker part of that cylinder that is going to withstand strain. Okay, so this same understanding is what we apply, especially in physiotherapy. They do calculations with stress and strain, because that is what actually affects the way the muscles and the bone are being stressed or strained or treated. The kind of load that can be applied that can lead to restorative or deformative effects. Okay, so we have an example on that. I would like us to look at think it's example 9.10 or so of our test. So just like we have seen, standard values of some materials, the Young modulus, for biological materials too have the standard value. We can see that when we said the larger the Young modulus, the more stiff that body is. We see the values of the Young modulus for rigid body far higher than what we have here. And it's following the same order too. The tooth is stronger, the enamel part of the tooth, okay? Because the inner part of the tooth also will respond differently to strain or stress. So we see the value also following the order of elasticity, stiffness of that material. So we also see the comparison of the tensile strength of such material. Remember, tensile strength is that description of the stress at its ultimate level. That is the point of breaking. So whenever you see tensile strength, it means that value beyond which this object is going to be permanently deformed. So we'll have in our test the example 8.9 to see how we use this information about stress and strain to describe or better understand the response of biological bodies to stretching and compressing. So I'm listening.
I just wanted to clarify,
Mm-hmm.
if that's okay. Those values, those are like for tensile strength and for the what's it called? The Young's modulus one. Would we be, those are like what's it called?
Constants.
Constants, yeah.
Yes.
And would we be given those if we were like asked a question on a
Yes.
test or something? Okay.
Yes, so
Thank
that's
you.
why it's coming like a table. You're not going to be asked to experimentally determine them. They have already been determined experimentally and given to us as table. Okay, so if you are asked to determine them, it means we just want a kind of comparison to the standard value that is already existing. Okay, so we should note this, that the difference between the plant and the rigid material is that they have large, the rigid is in their value, the large difference is in their value. The rigid one has higher modulus, Young modulus, while the plant has the lower value. Okay, so let's look at, we have looked at how stress, strain, and expansion also stating that biological bodies respond to these things that we are looking at, like they are theories. Now we want to pick one that we've seen before, like the force and tug. You remember what force is and what tug is. The force, when we looked at the last class thing before the last, the class before the last, we described tug and force and how they are related in a rigid body system for combination of motion. And we also saw definition for or the condition for static equilibrium in rigid body. Now the human body also follows that dynamic relationship of the rigid body where several kinds of motion happens at the same time. So how do we relate forces and tug in the human body? Well, we have examples, but we're not going to look at them. We just want to bring home the fact that if you are moving into biological sciences or engineering, this is where physics actually become beneficial to you, because most of the things you're studying, they are actually following the physical principles that are already developed and designed by physical laws as you study in physics. So tug is a kind of force that causes rotation. Remember that. And then the force is that which causes motion in the linear dimension. So we see the picture before us, the picture of the leg of two kind of animals, the skeleton of two kind of animals, the cat and the armadillos. So this is armadillo and this is the cat. Now, if you look at these two diagrams, fine. It appears as if two of them are bending the same way because it's taking the shape of the leg of an animal. But let's look closely to the structural arrangement of these bones. We see the shapes slightly varying, but will have some basic parts, just as it applies to every animal or shape of leg, something that is moving. Beyond the thickness, variation in thickness and variation in the structural arrangement, that is the angles, we want to notice another thing, or want to emphasize another thing, that the design is meant for the kind of or habitation or the kind of animal they are. For the cat, it's known for speed, okay? And it prey on other animals to survive. Okay, when we say cat, now we're not just talking about your cat at home. It can be the white cat, can be they all have the same shape and morphology. Then for this animal, we see it has this habit that it has to dig to fend for, to search for food. So its design here is such that it can easily dig. Why this one is designed such that it can easily move. Now, all this design that I'm talking about actually brought together the principle of tug and force. For such motions to happen, we see that a kind of force has to be applied to bring about a rotation of some parts of these bones around the pivot points. Okay, and we see that the one that is digging, the attachment to the pivot point here is kind of longer than the one that will make the spring motion, that is run fast. So this one is designed to be a jumper, has speed, but this one is designed to be a digger. All using God applied the principle of tug and force, which he later understood as tug and force in science, tug and forces in science, to create these things to serve the particular purpose. Okay, so now, and it is sometimes the study of this kind of animal that bring about invention in sciences. Okay, so that is what really does to the mechanical advantage. What do we mean by mechanical advantage? It means leveraging on existing principle to produce technologies or machines that can easily help us. Let's take the example of the nutcracker here. We see the design of the nutcracker looking more like bone, right? But it's not a bone. We actually see that from the analogy of this bone that we've previously seen, there are certain level of forces that can be applied around the pivot and it leads to the multiplication of certain force at different region. Okay, so if we take a look at this nutcracker, we see the handle extending. We can see the pivot here, the load, which is the nut we want to crack, very close to something like an opening like mouth. Just permit me to use that word, but it's not mouth. Okay, then the handle is long. Now the long handle is designed such that when you apply small force, it's going to yield, when you apply like, yes, let me use the word small force, it will translate around this pivot and yield a multiplied force that will lead to cracking of that nut. Okay, so The handle is designed with the understanding of static equilibrium that helps us with the fact that the forces acting on one direction, downward or sideways, will be equal for that object to be static. And also using the principle for the static equilibrium for a tug, the tug round a pivot all have to sum to constant for that object to be static. So we brought in those two principles to the design of the Nutcracker. We just leveraged on that idea. And this is how we keep leveraging on the ideas to design technology. So the idea behind the Nutcracker is that a small push is applied to give at the handle to give a big force that can bring about the cracking of that nut, such that when you try to do it manually, it's going to cost you more. But when you use this machine, it makes work easier. So you see, different forces acting and how we leverage on that to designing the Nutcracker. So let's see. So you notice that chapter 8 is more of the different application of what you have seen in chapter 5, 6, and 7. Okay. And just there's also an example on that we did not look at, that we ought to look at, but as usual, Wednesday's class used to be less heavy than Monday and Friday because of our lab. We're preparing for our lab, okay? So let's look at the very, more like the last part. Okay, some things that I didn't mention here. They're just the statistic of this basic design, small push giving you ×3 output of force and all that, okay? Okay, let's see what we can cover in the next 5 minutes. Yeah, that's about all, yeah. So in the next 5 minutes, we just want to look at stress versus range of motion and speed. And we're looking at this in terms of just the biological body. Yeah. Yeah, we have the example of the plier and all that. Good, very good. Okay. So we look at the last part, which is the stress versus range of motion and speed. Now, from this topic, we can see that from all we have understood, looking at the first animal, then the Nutcracker, there's something about the range of motion that relates to speed and then strength. Okay. So we'll quickly be looking at the elbow, the hand, and the jaw to understand this. Now, if we look at the jaw, like the jaw of the human and that of the dog, like I said earlier, what they are designed to do, determine the arrangement, and we maximize this arrangement or the geometry of their arrangement to show the difference of what they are meant for. But they are all going to maximize the fact that if the emphasis is on strength, the arrangement is such that the range of motion and speed might not be emphasized. But if the emphasis is going to be on speed, the strength, like those first two animals that we saw, the crucial difference is in their strength. It's obvious that the second animal is stronger than the cat. But when it comes to motion, the cat is going to fly compared to what that other animal's motion would be. So how does their strength and arrangement of strength vary with that of the motion and speed? So we see the pivot of the dog. This is where the strength is. We can see the distance. I'm just going to, by the time we see the next example, we'll see the human strength, the masseter muscle for the teeth when you chew, actually emphasize on the second to the last molar when you chew. And that the muscle helping you is here. And this is your pivot of your jaw. So We see the distance for this, and we see the distance for this, and the shape also, telling you, our biology, the kind of strength this one eats more flesh, and this one eats virtually everything, but has a way of manipulating everything it can eat. Okay, what is the word? Carnivorous, omnivorous, right? Okay, so we see this one because we did not make the simplified diagram for this. We'll better understand it here. That let's take example of the ankle, your leg. We see the muscle such that when you stand on your toes, when we talked about equilibrium, the center of gravity shifts to align directly with the base. When you stand on your toe, what happens to the tendons and the pivot? It is such that the distance between the pivot and the force on the toe, this one, the force is going to act upward. It's also going to obey the law of when you are standing, you are static. The forces around the pivot will be 0. And then if we present this to clearly see it in a simplified force diagram, we will see that the force on the pivot is 0. So when we wanted to express the torque on the pivot is 0, and the force acting upward is equal to the force acting downward for you to be able to stand on your toes. Okay, so we'll see in our expression of torque, only this and this forces were represented because this is acting directly on the pivot, so it's 0. So we'll have, remember the formula for torque. Okay, tau being equal to R and F. So you know the direction as well. Just a reminder of how we apply this to solving problem. Now the emphasis here is that the moment arm, look at the distance of the moment arm for the floor and the tendon is shorter than the pivot. Okay, so the moment arm, which is the range, which defines the range of motion, defines the strength. Okay, why it also influences on the speed. We emphasize that with the example of the elbow. If you look at the moment arm distance here, it's very small compared to the moment arm distance for the hand. So you see a larger motion on the hand than when you try to move your feet the same direction as your hand. You see the feet beside the length of the feet. The length kind of defines the motion. So remember when we were describing the first thing we talked about in compression, I said something about the length of that rod. The longer, the better for motion, if the emphasis is going to be on motion. But if it's going to be on strength, we'll be emphasizing a different length, okay? So that's how the length and the speed and strength relates. Okay. There's no pool for today's class, so we have 25 participants. I'm assuming that 25 of us were present. It's Michaela in the class. Osia Michaela. Last class, I was looking for you, but I didn't get response. Okay. Oh, good to see you today. All right. So by next class, we'll move to the next topic and we'll be preparing for our test. I should be able to put up assignment for today's chapter 8 today by the close of today. So look out for that on Moodle. All right. And the video, the lecture video, I just put I was tired of having to put the link every time, one. So I just put the YouTube link so you can always go there to check the lecture videos as well. Okay. If you have any question on our discussion so far from chapter 1 to chapter 8, feel free to check on me on that. Send me a mail. If you cannot see me in my office, can just always send me a mail and I'll reply it, or send a chat on Moodle too, and I'll reply. Okay. Okay.
All right, thank you.
Yeah, somebody's asking if they want to confirm if want to submit the assignment in the lab today. Yeah, you should come with your assignment to submit with the lab. The last lab also is due for submission today. All right, have a good day. See you in lab today. For those of you in Wednesday lab. Bye-bye.
All right, thank you. Goodbye.
Goodbye.